Okay, so thanks a lot for inviting me to give a talk. I should tell you, since we are a few seconds in advance, that this is my second talk during today, so I might be a little bit slow or fast, so don't hesitate to interrupt me with questions if you have some. So as I should say, this is my work in progress, meaning that I need to finish the writing, which takes enormous time during the pandemic period. But anyways, so let me start with just reminding all of you how prime number theorem looks. So by P and C, we know that the prime counting function P of x, which is the number of primes up to x, is asymptotic to the logarithmic integral of x, the integral from 2 to x dt over log t. And in that talk, I would like to consider an analog of this result for the hyperbolic plane. So let me model the hyperbolic plane, and I would like to consider an upper half plane H, which is the set of z, complex z x plus yi, where x is in R and y is in R plus. Okay, so then let me define gamma, which acts on my H, which is SL2 of Z, and this is the set of matrices 2 by 2 matrices x1, x2, x3, x4, such that all x1, x4 are integers, and we have the hyperbolic condition x1, x4 minus x2, x3 is equal to 1. So this is what I call the hyperbolic condition. I will call it by this name many times. So, okay, so then gamma acts on H by fractional linear transformation. Let me define you the distance function, because we anyway need it, so let me write it. So we define distance function d of z and w as the z minus w squared divided by imaginary part of z, imaginary part of w. And also let me take as the origin the point z equals I, and call the orbit, so orbits gamma times I, where gamma is in gamma, which is SL2Z. So we call those orbits integers. Okay, so let me state the first, let me state the theorem in its first shape, and then I will reformulate it in a more convenient shape. So this shape is more or less geometric. So this is the main, kind of main result that I would like to talk today about. So we let S sub gamma of x to be the number of points gamma I, be the number of points gamma I at a distance n minus 2 from the origin. So at a distance n minus 2 from the origin. So from the from the origin, and also we would like to require with n going up to x being free of squares. So mu square of n is equal to 1, where mu is the Möbius function. So this means that S sub gamma of x, thus S sub gamma of x, it just counts the number of quadruples x1, x2, x3, x4 in Z4, such that n is equal to the sum of 4 squares, plus x4 square up to x, and we have the hyperbolic condition x2, x3 is equal to 1, and in addition we have mu square of n is equal to 1. So then for as x goes to infinity, then let me say for x larger or equal than 2, we have S sub gamma of x is asymptotic to x, meaning that we can find two constants C1 and C2 larger than 0. I write it for a purpose such that C1x less or equal than S sub gamma of x less or equal than C2 of x. Okay, So this is the basic result I would like to talk about. And as you can imagine, since here we have square free numbers, which are of positive density and hence they're easy to deal with. Of course, we would like once you manage to prove such a theorem, you would like to get an improvement over that. So you would like to consider, instead of just square free numbers, the square free numbers with prescribed number of prime factors, and then you would like to reduce the number of prime factors down to as low as possible. If you manage to get one, you get the primes. Usually you don't, but here it seems that you are allowed to prove the same type of result by the same technology, going with square free numbers with no more than 3 prime divisors. So seems that the same kind of technology should work. So let me actually discuss briefly like what is known about this kind of result. So first of all, of course, you can ask yourself what happens if you change the condition of n being square free to the condition that n is a prime. So let me define p sub gamma of x. Let this one count primes in S sub gamma of x. So this means that P sub gamma of x is the number of quadruples x1, x2, x3, x4 in z to the 4, such that P is equal to the sum of 4 squares up to x, such that x1, x4 minus x2, x3 is equal to 1. So this is a much harder question. And it was kind of resolved by Friedlander-Ivanets in the paper that is called Hyperbolic Prime Number Theorem. I think it was in the beginning of 2000s, something like 2005 or 2006, something like this. So let me state this theorem, and then I will explain. So the theorem of Friedlander-Ivanets. Okay, so if we assume that some conjecture holds, then as x goes to infinity, we have the following bound. C1x divided by log x is less than p sub gamma of x is less than C2x divided by log x. And this one is unconditional. So the upper bound, the upper bound is, as it often happens, is unconditional, but the lower bound is conditional, and this is the problem. So this is conditional, and this is subject to the condition that I will tell you about. So this condition is basically interpolates between Bombieri-Vinogradov. This is called A of theta. So this interpolates between Bombieri-Vinogradov and Elliott-Halberstam. So what is important here? So we get, as the upper bound is easy, the upper bound is unconditional. The lower bound essentially uses something like Riemann hypothesis for curves. So when we are trying to prove our theorem, we allow, instead of primes, to have square free numbers. This means that our level of the distribution is going to be much higher, and this means that we kind of have the condition A of theta automatically for larger theta than for the primes. So this is the motivation why everything would work. But let me formulate who is A of theta. So we must assume A of theta for subject to A of theta for some theta smaller than 1, right? But close to 1. I will come back to this point later. So, and then Friedlander and Ivanets showed this upper and lower bounds. Okay, so now who is the conjecture A of theta? Well, this is kind of usual stuff. So conjecture A of theta is between Bombieri-Vinogradov and Elliott-Halberstam. So let me recall you. So we have psi of xqa, which counts, A and q are as usual coprime. So we have psi of xqa. This counts over arithmetic progressions lambda of n. So this is essentially the prime number, the prime counting function in arithmetic progressions with logarithmic weight. Then, of course, by the prime number theorem in arithmetic progressions, we know what to expect from the main term. And let me denote the remainder term, E of xqa, for the individual q as psi of xqa minus what we expect from that. So we expect this to be psi of x divided by phi of q. Psi of x is x, so we can just subtract x divided by phi of q. Okay, so, and let me actually, since I'm going to talk about the average, the assumption about averaged error terms, so let me define the remainder of level q. So the remainder of level q, sorry, my q and theta, they look pretty similar, which is e of x q. This is the sum over q up to capital Q, maximum over a such that a and q are coprime, maximum over y up to x, e of y q a. So we average the error term in the prime number theorem and arithmetic progressions over moduli up to capital Q. When our capital Q is small, so when the moduli are small, we know by Ziegel-Wolfish the estimate for the individual moduli. When moduli are large, life is harder. So now we have introduced this parameter theta, which is between 0 and 1, and we introduce the following assumption. Assumption A of theta, well, or hypothesis A of theta tells us that E of xq is less than x divided by log x to the a, where a is some constant larger than 0, and this holds for q, which is equal to x to the power theta minus epsilon. So this holds for every epsilon larger than 0, every a larger than 0, where the implied constant depends only on epsilon and a. So here I can put epsilon a below the Vinogradov sign. So this is the conjecture A of theta that Friedlander and Ivanez used for the lower bounds. So we could say that A of 1/2 is actually the Mambieri-Vinogradov theorem. So this is known. So we can also say that A of 1 is Elliott-Halberstam conjecture, which is not known. And the best we know about the primes is actually A of 1/2, which is Mambieri-Vinogradov. So this means that for Friedlander-Ivanez, in order to manage to do something, you need to overcome this 1/2 in a way. You need to make it a little bit better. But once we start to talk about the square free numbers, so what we do, of course, we are trying to proceed in the same way for the lower bound. The upper bound in our case, meaning so this one is going to be sort of easy, and this one is going to be sort of harder because we now want it to be unconditional. But since before, for the conditional results, Friedlander and Ivanez, they used this level of the distribution of the primes given by the Mambieri-Vinogradov, then this means that we are in a better shape because we are allowed ourselves to have only square free numbers which have better level of the distribution. So this one is like lower bound CIF. Well, plus, so to say, I will call it A prime of theta because I don't want to write it explicitly. So we need to use the lower bound CIF, plus we need to use the analogous, not conjecture, but the analogous proven results for the square free numbers in arithmetic progressions. So what we know about the square free numbers in arithmetic progressions? Well, SQ3 in arithmetic progressions. So of course, as usual, we are going to take A and Q coprime. Then if we look, well, I will actually denote this as E mu squared, their term, xqa. So the individual one is just the sum over n up to x, n is equal to A mod q mu square of n, the characteristic function, minus 1 divided by q, sum over n up to x, mu square of n, right? Well, okay, let me write it more precisely. So 6x pi square q, product over p divides q, 1 minus 1 over p square to the power minus 1. Okay, so this is the error term in the square free numbers in arithmetic progressions. So what we know about the individual case for the individual moduli, so we know that Hule, I think this is the best up to date, showed that this one, satisfies the bound big O of epsilon of x over q to the power 1/2 plus q to the power 1/2 plus epsilon. And this holds, so here the constant, the implied constant in the big O depends only on the epsilon, and epsilon is arbitrary. So note that the trivial bounds for this one would give you something like e mu square of the same thing is bounded above by x over q plus 1. Yep. Okay. So, and then what we need, so this is the individual case, like, which is usually not the best we can hope for. So, and then the recent, well, fairly recent result, the best I know, if you know something better, tell me. So, by Kuish, Parlinsky, and Zhang, I don't remember the year. So they showed that if you sum over q up to x to the 3/4 minus epsilon, e max mu square of x q, then you get the saving, power saving in the on the right hand side. So here e max mu square of xq is of course just the max over a and q coprime max over y up to x e mu square of x y, sorry, qa. So complete analog of the a of theta. Okay, so the advantage that we have here is that we have something that is much better than 1/2 minus epsilon. We have 3/4 minus epsilon, and moreover, we have a power saving here. So this makes our life easier in the sense of the application of the conjecture. So we could proceed in more or less analogous way for the square free numbers, but we should bear in mind what kind of the level of the distribution we can allow ourselves. There are more cases inside, but this is a technical detail. Like 3/4 are not as good as one expects from the first point of view. But anyways, 3/4 is much better than having, I don't know, like say 1/2 plus something. Anyways, so let me actually just, while I have like 15 minutes, let me just tell you like the generic beginning without any kind of technicalities, the generic beginning of the proof of the square free case. And once you try to control the number of the prime factors, you do basically the same, but you introduce the additional function that counts the number of prime factors that you need to use this, that its support is like sort of small. Anyways, so let me recall that in S1, so back to the proof. To the proof of theorem. So for the square free case. So we recall that we actually count n that is written as this one up to x, subject to the hyperbolic condition, which is x1, x4 minus x2, x3 is equal to 1. And of course, we have mu square of n is equal to 1, but don't worry about this so far. And our goal is to show that S sub gamma is asymptotic to x. The upper bound, of course, is trivial because just the number of square free numbers up to x is asymptotic to x, so the upper bound is cheap. For the lower bound, we are going to apply the lower bound sieve, but first we are going to make everything look suitable for the upper bound sieve. So we change variables, we make just the linear change. x1, x4, y2 is equal to x2 minus x3, and y3 is equal to x1 minus x4, y4 is equal to x2 plus x3. This allows you to compute x's in terms of y's, of course, and you know that if n is an odd integer, then xi is an integer implies that yi is an integer, and converse is also true. So this means that the number of integer solutions in x's is the same as the number of integer solutions in y's. Okay, so then when we actually rewrite this condition, that n is equal to the sum of 4 squares, when we rewrite it in y's, then we get that y1 square plus y2 square is equal to n plus 2, and y1 square plus y2 square minus y3 square plus y4 square is equal to 4 mu square of n is equal to 1. Okay, so then this condition can be written as y3 square plus y4 square is equal to n minus 2. Okay, so we got here n plus 2 n minus 2 equals to the sum of squares equals to the sum of squares. So this means that we reduced our problem to counting the correlations of the function that counts the representation as a sum of two squares. So let R of n be the number of ways to write n as a sum of two squares. So then what we do, we note that S sub gamma of x by this change of variables is bounded from below. Well, I lose the factor of 4 since this is equal to 4 times sum over d divides n chi 4 of d, but I lose the factor 4 here. So this is the sum lower bounded by the sum over n up to x, r of n minus 2, r of n plus 2, mu square of n. Okay, then this means that the theorem that we would like to show is equivalent to showing that this thing is bounded below by x. And the lower bound is something that we assume that we achieve by the upper bound sieve. So first of all, we note that if we look at the m, so, well, maybe I should write if. So if m is such that p divides m implies that p is equal to 1 mod 4, then the character chi 4 is just 1. And then this means that r of m is going to be equal to 4 times tau of m, where tau of m is just the divisor function. D divides m 1. Okay. So, and then since we are in the lower bound, then our life is just much easier. So what we are going to do is we are going to say that for any, hence for any positive integer n, for any m in Z plus, we have that R of m is bounded from below by 4 times tau of m times b star of m, where b star is 1 if p divides m implies that p is equal to 1 mod 4 and 0 otherwise. So b star is non-zero precisely when m is an odd number that has a primitive representation as a sum of two squares. Okay, we are going to use this bound for m equals n minus 2. So we look into our S sub gamma of x, and we just lower bound it by sum over n up to x over square free numbers. I think n must be square free. Yes, b star over of n minus 2. R of n plus 2 stays as it is, tau of n minus 2, and let me write here mu square of n. Okay, so then I'm going to write this tau as the, so this is the divisor function, so this means that this one is equal to the sum over delta divides n minus 2 of 1. And then, of course, I'm going to invert the order of summation, so delta would go up to x minus 2, right? And I'm allowed to write here, well, I lose the factor of 4. So delta is going up to a new parameter capital delta. There I have b of delta, and here I have sum over n up to x. N is equal to 2 mod delta because n minus 2 was divisible by delta over square free values of n. B star of n minus 2 times r of n plus 2 mu square of m. So here, this parameter capital delta, where delta, which depends on x, is, let me say, x to some power, and what we need, mu is, well, smaller than 1 officially, so to say, but we could take it as small as we want because we are in the lower bound setting. And then what remains is just to, so we have the internal sum, and the internal sum looks like this. So we have sum over n up to x, n is equal to 2 mod delta, b star of n minus 2, r of n plus 2, well, mu square of n. So to this one, we can already apply the classical sieve. So here, apply classical lower bound sieve. So here we can apply the classical lower bound sieve, and this would allow us to get the lower bound for this quantity in terms of R of n plus 2 times R of n minus 2 in the arithmetic progressions. And sorry, in terms of mu square of n in the arithmetic progressions. But we know, and then we know the error term in the error term in the distribution of the square free numbers in the arithmetic progressions. We know this by this result of Sparlinsky and other people. We know it up to quite a good level of the distribution, and then this is the usual routine to adjust the level of the distribution so that everything works. The main trick here is to apply this kind of lower bounding in a clever way. And yes, if you want to do it, yeah, it's, of course, I'm lying you a little bit because you need to keep a very good track of the error terms and their dependence on the moduli, because you cannot allow yourself to lose this dependence. But morally, this is basically what happens. Okay, so if you want to adjust it to the case when you count not only square free numbers, but numbers that have not more than this amount of the prime factors, then you need to have some better results for the error term on average, some better analogs of the conjecture of A of theta. And this also could be done because some of them are available, though the level of the distribution is of course worse than 3/4, and you need just to worry a lot more when you are carrying out the error terms that are introduced here when you apply the classical lower bound sieve. So, well, morally this is, well, yep, morally this is what happens. So yeah, another technical moment that I wanted to tell you is that it seems that you kind of lost this here square root of log, but you are going to gain it again here. So overall you are going to get the correct bound. Okay, so I think that I have like maybe a few minutes left, and since I don't want to give you any kind of hard technical details, then I would prefer to answer some questions.
You have 3 minutes.
Okay, so you want to hear some continuation. Okay. Okay, so let me tell you briefly so what we are going to have. So first of all, this is the sum of S of delta, and S of delta of course can be rewritten. So S of delta, if you change the variables, can be rewritten as the sum over m going to x minus 2. M is equal to 0 mod delta. Now you have B star of m times AM, where your AM has all the information that you need. So this is R of M plus 4, because you are going to shift now, M goes till x minus 2. So this means that M is equal to n minus 2, and you had n plus 2 before. So here you have m plus 4 and mu square of m plus 2. Okay, so in order to apply the sieve methods, you need to know the partial sum of this one. The partial sum of this one is doable. So this means that what you will do, yep. So you would need the following thing. You would need to be able to have this one, m plus 2 is equal to a mod q of am. And this is just equal to the sum over n up to x. N is equal to a mod q r of n plus 2 mu square of n. And this is just a modification of the of how you count r of n plus 2 multiplied by lambda of n. And this is equal to hx, where h is an absolute constant, times cq plus some remainder term. Let me call it r sub q of x. This constant CQ is actually quite nice. If you look at it, it's going to be a nice function. So it's going to be like q divided by the generalization of the Euler totient function. So q divided by g2 of q times some Euler product. So these constants here, they are nice and they are meaningful. But what we also know is that we know that the error term r sub q of x is going to satisfy the estimate sum over k up to root x Emax of x for d delta k plus root x. And then the important part is to make this small. So if we manage, so we need level of the distribution good enough to make this small, to make the moduli, to make this, well, let me call it suitable. So to make, what happened? Yep. I don't know, sometimes my, okay, now it's better. Yeah, so we need to make, this is just the, when you are going to recover all the divisibility conditions, you are going to have the moduli that depends on d, delta, and k. And you would like to make all of them fit inside the final estimate for the remainder term. And because here, I recall you, because where was that? Yeah, here. Yeah, and because here we had x to the 3/4, and still we got quite nice power savings. So in this problem, we don't need to care about logs at all. So since here we got 3/4, this means that we are far away from x1/2, and we are in a good position. So we could adjust all this d, delta, and k to be as a product to be small enough so that we can apply our estimate on average. And then we could actually bound the contribution of the smaller ones just out, because we are talking about the lower bound, not about the upper bound, since the upper bound is sort of trivial. So basically this is what you need to do. So this is how you get the estimate for the s of delta. So by the lower bound if you got an estimate for s of delta. And then from s of delta, you need to go back to the, you are going to sum this over delta up to the capital delta with the multiplier b of delta. So, and then you have to adjust this capital delta to be small enough. This is another like a kind of the level of the distribution fact. And yep. And this, well, of course, this capital delta is going to be x to the power of mu, and you are going to take like mu, I don't know, I don't remember, like 1/6. So in reality, let me say, so mu is going to be like x to the 1/6, something like this. So, and then you just, since you are in the lower bound, then you can throw away everything that you want, and you just make mu to be small enough so that when you take the product over all of this, the remainder condition is still satisfied. So I'm sorry, I know that it's very technical, but I hope that at least the idea of what you are trying to do was clear.